In application of numerical methods, there are two types of errors that we will focus on. One is truncation error and another is round off errors. What is truncation errors? An approximation is often used in place of an exact mathematical procedure. For instance, consider the Taylor series expansion of, say, sin x. That is equal to x minus x cubed by factorial 3, this, and so on. There are infinite number of terms. But practically we cannot use all of the infinite number of terms for computing sine of any given angle x. So what we do? We usually terminate the process after a certain number of terms. The error that results due to such a termination or truncation is called truncation errors. Hence consider e to the power x, which is an infinite series, this. So there are infinite number of terms, but practically we cannot use all those terms, we cannot consider all the terms. Suppose we want to use 3 terms to calculate e to the power x. That is, we want to approximate e to the power x as considering 3 terms of its expansion. Then the truncation error for such an approximation is this. This is equal to this. Now the second type of error, that is round off errors. Since computers can use a fixed number of digits, for this purpose of calculation we have to discuss a given number of digits of a given number x. So we have to approximate x discarding a proposed number of digits. Thus we get approximate value of x. The rejection of unwanted digits are done in a rational manner. The process is known as rounding off errors. We follow some rounding off rules. What is this? Suppose x is a given positive real number. In the usual decimal system, x can be written as this. It's a floating point number. This is the part before decimal and this is the part after decimal. Now we want to represent x by retaining digits up to, say, q places of decimal. Write it in this way. So we want to return x up to this decimal places, q places of decimal. Then 3 cases can arise. Case 1 is, what is this number, this digit? The digit after this place. Suppose this number be any one of this number 0, 1, 2, 3, 4, any one of this. Then what will happen? Then the remaining part, we just discard the remaining part without changing anything of the parts before that. That is, in this case x gets approximated as just simply discard all the digits after the qth place of decimal. For example, consider x to be 75.23489, and if you round up this number up to second decimal place, that is this place, then what we do, we just look after this decimal places the number 4, that is the third decimal place. It is 4, that is any one of this number, so it gets approximated to, after rounding off, it gets approximated to this. Just discard this number. Now consider case 2. We want to round off up to this decimal place. So we have to consider this number. Suppose this number, this digit is equal to any of 6 or 7 or 8 or 9. Any of this. Then what happen? then x is approximated to that is we increment this number. For example, let x be this, and we want to round up x up to third decimal place, that is this. Then consider the fourth decimal place. What is the number? This is 8. Hence this is any one of this. So what we do? We just increment this number. So x gets approximated to 75.235. Last case is case 3. That is, if this number is equal to 5 and also let it be followed by at least one non-zero digit, then x is rounded to this. But it is that if this number is 5, but if this is the last non-zero digit, that is there is no other non-zero digit after this digit, then what will happen? Then two cases are there. One is if a minus this number is even, then x is approximated to this, and subcase 2 is that a minus q is odd, then x gets approximated to this. Consider an example. Let x be equal to 75.5678500 and round up this number up to 5th decimal place. No, say up to 4th decimal place, that is up to this. Then consider the 5th decimal place, this is 5, and see this is the last non-zero digit. Hence just look after this digit. This is even, hence subcase 1 is applicable. So x gets approximated to 7, 8. But suppose x is this 500 and round up the number x up to 4th decimal places. Since 5th decimal place there is 5 and this is the last non-zero digit, we look at the 4th decimal places, it is odd, so subcase 2 is applicable and x gets approximated to increment this digit a. Next is absolute, relative and relative percentage of errors. Let v suffix t denote true value of a number x and v suffix a define approximate value of number x. Then absolute error, that is EA, is written as equal to mod of this. Relative error is written as ER, that is equal to absolute error divided by the true value. So that is equal to divided by VT. And relative percentage of error, that is written as E suffix P, is equal to this. Note one thing, if a number be rounded to m decimal places, if a number be rounded to m decimal places, then absolute error is less than equal to this. Another theorem I will state here without proof is that if a number be rounded to n correct significant figures, then relative error is less than 1 by this quantity, this is 10 to the power n minus 1, where k is significant figure in the number.